Have you ever wondered how sediment volume is estimated in a settling basin? We're delving into the depths of sediment volume estimation, a key process in the operation of hydropower plants. It's a fascinating journey that takes us through regular sediment sampling, meticulous analysis, and understanding the inflow rate. It's a science that helps us balance the intricate dance of inflow and deposition rates to keep our hydropower plants running efficiently. This process is crucial in maintaining the efficiency of a hydropower plant. Estimating sediment volume involves several steps, starting with sediment sampling. This regular procedure is essential to keep tabs on the rate of sediment accumulation in a settling basin. Think of this as a routine checkup, where samples are gathered from various locations within the basin to get a comprehensive view of the situation. Then comes the sediment analysis, which is like the lab work following our routine checkup. Here, the collected samples are examined to determine their density, grain size distribution, and settling characteristics. This data forms the bedrock of our volume estimation, giving us insights into the amount of sediment that has settled over time. Next, we need to determine the sediment inflow rate. This is based on the inflow characteristics of the river or stream feeding the basin, coupled with historical data. Imagine it as the rate of incoming traffic, the number of sediments entering the settling basin per unit time. Finally, we calculate the sediment accumulation rate, which is the difference between the sediment inflow rate and the sediment deposition rate. It's like a seesaw balance. On one side we have the incoming sediment, and on the other the sediment that's actually settling down. By comparing these two, we can estimate the volume of sediment that has settled in the basin. And how do we do that? Well, we use a simple formula. The volume of sediment equals the difference between the incoming and outgoing flow rates, multiplied by time. It's like measuring how much water is left in a tub after you've been filling it up and draining it simultaneously for a certain period. So, there you have it. From taking sediment samples to crunching the numbers, that's how we unlock the mystery of sediment volume estimation. It's a combination of fieldwork and math, giving us the tools we need to maintain the efficiency of our hydropower plants. By comparing the sediment inflow rate to the sediment deposition rate, we can estimate the volume of sediment that has settled in the basin. Now let's delve into the formula that helps us estimate the sediment volume. This mathematical model is not just a set of symbols and numbers, but a tool that enables us to predict the sediment accumulation in a settling basin over time. The formula we use is volume of sediment equals the difference between the flow rate of incoming water and the flow rate of outgoing water, all multiplied by time. In simpler terms, it's V underscore S equals Q underscore in minus Q underscore out times T. Let's break it down. V underscore S, or the volume of sediment, is what we are trying to estimate. This is the total amount of sediment that has settled in the basin over a given period. Next, we have Q underscore in and Q underscore out. Q underscore in is the flow rate of incoming water measured in cubic meters per second. This is determined by the inflow characteristics of the river or stream, as well as historical data. Q underscore out, on the other hand, is the flow rate of outgoing water, also measured in cubic meters per second. This value takes into account the water that leaves the basin, either through evaporation or through the outflow channel. The difference between Q underscore in and Q underscore out represents the net volume of water and sediment entering the basin. If more water is coming in than going out, the excess water brings along sediment that eventually settles at the bottom of the basin. Finally, we multiply this difference by time, denoted as T. Time is the duration over which we want to estimate the sediment volume, typically measured in seconds. By calculating this formula, we are essentially measuring the rate of sediment accumulation in the basin. It's important to note that this formula provides an estimate, not an exact value. It's based on the assumption that the rates of inflow and outflow, as well as the sediment characteristics, remain constant over time. So there you have it. The math behind estimating sediment volume is straightforward, yet powerful. This formula provides an estimate of the volume of sediment deposited over a specific period. It's a guide, a compass, helping us navigate the often murky waters of sediment management in hydropower plants. Once we have the sediment volume, it's time for the cleanup through a process called flushing. Flushing is the act of releasing a controlled amount of water from the settling basin, which carries the sediment with it. This process is usually scheduled during periods of low demand to prevent any disruptions to power generation. The released water, heavy with sediment, is channeled through a flushing outlet. This ensures that the sediment-laden water is safely released downstream, preventing it from re-entering the settling basin and causing further accumulation. Flushing is essential to the operation of a hydropower plant. Without regular flushing, sediment would build up, reducing the basin's capacity and efficiency. It's like cleaning your house. If you let the dust accumulate, it will eventually become overwhelming and hinder your daily activities. Similarly, excessive sediment buildup in the settling basin can severely impact the functioning of a hydropower plant. The frequency of flushing is determined by a variety of factors. First, the rate of sediment accumulation in the basin. Faster accumulation rates may require more frequent flushing. Second, the design and capacity of the settling basin. Larger basins may require less frequent flushing. Third, the potential environmental impact of flushing. It's important to consider aquatic life and downstream ecosystems during the flushing process to minimize any adverse effects. The hydropower plant's operation also plays a role in determining the flushing frequency. For instance, during periods of high power demand, flushing may be postponed to ensure uninterrupted power generation. The flushing flow rate is typically calculated as a fraction of the flow rate of the incoming water. This fraction, known as the flushing factor, is determined based on the desired flushing frequency. It ensures that the basin's sediment volume does not exceed its design capacity. In essence, flushing is a carefully calculated and controlled process. It's about striking a balance, removing sediment efficiently, to maintain the basin's capacity while minimizing the impact on power generation and the environment. Flushing is essential to maintain the capacity and efficiency of the settling basin. So how do we calculate the flushing flow rate? Well, it's simpler than you might think. It all comes down to a formula. The flushing flow rate, which we'll call Q_flush, is calculated as a fraction of the flow rate of the incoming water, or Q_in. In mathematical terms, that's Q_flush equals F times Q_in. So what's this F we're talking about? It's the flushing factor. It's a fraction typically in the range of 0.1 to 0.2 that's determined based on the desired flushing frequency. Essentially, it's the portion of the incoming water used for flushing. Let's break this down a bit. First, we have the incoming water flow rate, or Q_in. This is the volume of water entering the settling basin per unit of time, typically measured in cubic meters per second. This value is determined by the inflow characteristics of the river or stream feeding the basin. Next, we have the flushing factor, or F. This is a fraction that represents the portion of the incoming water used for flushing. The exact value of the flushing factor depends on a variety of factors, including the rate of sediment accumulation, the design of the basin, and environmental considerations. The product of Q_in and F gives us the flushing flow rate, or Q_flush. This is the volume of water used to flush the sediment from the basin per unit of time. So why is this important? Well, by controlling the flushing flow rate, we can ensure that the volume of sediment in the basin does not exceed its design capacity. This helps maintain the efficiency of the basin and, by extension, the overall operation of the hydropower plant. Remember, the goal of flushing is to remove accumulated sediment from the settling basin without disrupting power generation or causing unnecessary environmental impact. By calculating the flushing flow rate using this formula, we can achieve this goal in a controlled and efficient manner. The flushing factor ensures that the basin's sediment does not exceed the design capacity. The frequency of flushing is as crucial as the process itself, but how often should it be done? The answer isn't a one-size-fits-all solution. It's influenced by a myriad of factors, each contributing to the fine-tuned balance of a well-functioning hydropower plant. Firstly, the sediment accumulation rate plays a significant role. The quicker the sediment builds up, the more frequently flushing needs to occur. This rate is primarily influenced by the inflow characteristics of the river or stream feeding into the basin and can fluctuate based on seasonal changes and weather patterns. Secondly, design parameters of the settling basin itself also dictate the flushing frequency. Bigger basins can handle larger volumes of sediment and therefore require less frequent flushing. The design also includes the basin's ability to withstand frequent flushing without causing structural damage. The third factor to consider is the potential environmental impact. Flushing can disrupt aquatic life and downstream ecosystems, so it's essential to plan the process to minimize these adverse effects. Depending on the local ecology, this could mean adjusting the flushing frequency to times of the year when the impact would be less detrimental. Lastly, the operation of the hydropower plant itself influences the flushing frequency. Flushing can temporarily disrupt power generation, so it's often scheduled during periods of low demand. In essence, estimating the flushing frequency is a delicate balance of various factors. The frequency of flushing is a crucial aspect of managing sediment in a hydropower plant.